In electrical machines, whether it is motor or generator, the energy conversion takes place through the magnetic field. So it is necessary to understand the basics of magnetic circuits. Now let us consider the simple magnetic circuit here, wound with n number of turns, through which current I is flowing and the flux phi is set up. To supply current to this circuit, we need to have one voltage source connected in series with a resistor. This resistor is variable and it controls current through the circuit. We know that flux is proportional to the product of current through the winding and number of turns in the winding, and this product is called as the magnetomotive force. That is, if I increase current, the flux also increases, and if I decrease current, the flux decreases, and the current can be controlled by varying the resistance of the circuit. Especially to understand the three-phase induction motor working, we need to first understand the concept of rotating magnetic field. To understand this, let us consider a three-phase winding which is having equal number of turns in it, and all the three-phase windings are 120 degree apart in space. So here is the winding. So to this balanced three-phase winding, now if I supply three-phase balanced voltage of frequency f hertz, then it would produce a rotating magnetic field in the space. The magnitude of this rotating field is constant, and the speed at which it rotates is called synchronous speed. Now we'll write it in words. A balanced three-phase winding supplied with three-phase balanced voltage produces rotating magnetic field of constant magnitude. The speed at which rotating magnetic field rotating magnetic field rotates is called synchronous speed. It is given by n is equal to 120 times f divided by p, where f is frequency of supply voltage. P is number of poles for which the three-phase winding is made. To understand the concept of number of poles here, let us consider a single phase winding through which some current is flowing to produce a flux. It will have two poles, one N, another S. If I split this winding into two coils, then four poles will be produced. This idea may be extended to our three-phase winding also. So poles obtained by splitting three-phase winding is presented by P in expression for Ns. Now we will give the proof for production of rotating magnetic field by three-phase winding supplied by balanced three-phase voltages. Let us consider three-phase balanced winding supplied with three-phase balanced voltages. R phase voltage VR equal to Vm sine of omega t plus 90 degree, Vy equal to Vm sine omega t minus 30 degrees, B phase voltage Vb equal to Vm sine omega t minus 150 degrees. We'll number these equations as 1, 2 and 3 for future usage. These three voltages will circulate three-phase currents in three-phase winding. If we assume all the three windings are purely inductive, that is neglecting the winding resistance, the currents in three windings will be lagging these voltages by 90 degree. So now we'll write the expressions for the three-phase currents. The three-phase currents circulated by the three-phase balanced voltages will be lagging by 90°. The respective phase voltage we will write assuming winding resistance to be negligible. These three-phase currents are given by IR equal to Im sine of omega t, Iy equal to Im sine of omega t minus 120 degrees, Ib equal to Im into sine of omega t minus 240 degree. We'll call these expressions of currents as equation 4, 5 and 6. Knowing flux produced is proportional to current I, we can write expressions for the fluxes produced by three-phase windings. Looking at expressions of currents, flux produced by R-phase winding, phi m into sine of omega t, phi y equal to phi m into sine of omega t minus 120 degree, phi b equal to phi m into sine of omega t minus 240 degree. Here just we are replacing IR by phi r, Im by phi m, similarly Iy by phi y and Ib by phi b because of proportionality relationship. These equations we will call as equation number 7, equation number 8 and equation number 9. Putting omega t equal to 0 degree, 120 degree and 240 degree in equations 7, 8 and 9, we get interesting results. So at omega t equal to 0 degrees, equations 7, 8 and 9 become phi r equal to phi m sine of 0, that is equal to 0. Phi y equal to phi m sine of 0 minus 120 equal to minus 0.866 phi m. Phi b equal to phi m sine of 0 minus 240 degree, that is equal to plus 0.866 phi m. Representing these three fluxes, by phasors, we'll show first here the three phasors 120 degree apart, and we'll name them as phi y, phi b and phi r, and we'll show the positive directions of all these three fluxes. Phi r is 0, so it is shown with the dotted line. If I reverse phi y, I get minus 0.866 phi m. By completing a parallelogram, we add minus 0.866 phi m and plus 0.866 phi m to get the resultant flux, which is the diagonal of a parallelogram, which is in actual a rhombus. Let us name this B, A, D, and draw a perpendicular to diagonal from A. Call this as AC. Common point we'll call as O. We'll write what we have done in the figure above first. From A, draw AC perpendicular to OB. In rhombus OABD, angle AOC is equal to 180 degree minus 120 degree divided by 2. Reason is, in a rhombus, diagonal bisects the opposite angles. Now, in triangle ACO, cos of angle AOC equal to OC upon OA, that is cos 30 equal to OC upon 0.866 phi m. OC equal to 0.866 phi m into 0.866, it is cos 30 value. Multiplying, we get 0.75 times 5m. Since in a rhombus diagonals bisect each other at 90 degrees, two times OC is equal to OB. From figure we can write this. So OB is equal to 1.5 times 5. Resultant flux is given by OB, therefore phi RES equal to 1.5 times 5m. We will number it as equation 10. Second case we will take now at omega t equal to 120 degrees. Equations 7, 8 and 9 become phi r equal to phi m sine of 120 degree equal to 0.866 phi m. Phi y equal to phi m sine of 120 minus 120 equal to 0. Phi b equal to phi m sine of 120 minus 240 equal to minus 0.866 phi m. Representing these fluxes by phasors, here at omega t equal to 120 degrees, phi y value is 0, phi r is having 0.866 phi m value, and phi b is minus 0.866 phi m. Minus 0.866 phi m can be obtained by reversing phi b by completing parallelogram and drawing its diagonal. We get the resultant flux, that is phi RES. For that we have to perform same mathematical analysis. So we can directly write on the similar lines phi RES equal to 1.5 times phi m Now at omega t equal to 240 degrees, equations 7, 8 and 9 become phi r equal to phi m sine of 240, that is equal to minus 0.866 times phi m. Phi y equal to phi m sine of 240 minus 120, that is equal to plus 0.866 phi m. Phi b equal to phi m sine of 240 minus 240 degrees, equal to 0. Representing these fluxes by phasors, with phi b 0, I'll keep it dotted line. Phi r is having negative value at omega t equal to 240 degrees, so we have to reverse it. At the head of reversed phi m, we will write minus 0.866 phi m. Phi y is plus 0.866 phi m. We have not written phi r here, so phi y is equal to 0.866 phi m. To get the resultant flux, we need to add minus 0.866 phi m and plus 0.866 phi m. So phi resultant is now diagonal of the parallelogram or a rhombus. Don't forget to write angles as 120 degrees. Phi b, just direction I have shown, it is having 0 value at omega t equal to 240 degrees. So now similarly, phi resultant is 1.5 times phi m. To make use of any equation, we have to write numbers correctly. Just we will have a check once. Yes, here we have not written number, so we will number it as equation number 11, and then we will call it as equation 12. Now once again we will look at all the phasor diagrams. First phasor diagram, at omega t equal to 0 degrees, the resultant flux is horizontal. In the second phasor diagram, for omega t equal to 120 degrees, the resultant flux, which was horizontal, has rotated by 120 degree. Here we have not written phi res. Third phasor diagram, at omega t equal to 240 degrees, once again the resultant flux has rotated by 120 degrees. Now looking at equations 10, equation 11, and equation 12, we can conclude that the rotating magnetic field of constant magnitude equal to 1.5 m is produced when a three-phase balanced supply voltage is applied to a three-phase balanced winding. So I have to put it in proper wordings now. Now we will put our discussion in words. From equations 10, 11 and 12, and the three phasor diagrams it may be understood that a rotating magnetic field of constant magnitude is produced when a three-phase balanced winding is supplied with three-phase balanced voltage. In the next part, we will study the working principle of induction motor and then the construction of different types of induction machines.